Hello, I'm Jarod Johnson. I'm the architect responsible for open source HPC management software at Lenovo. Today I'm going to be talking about our work on Confluent. So what does Confluent do? It provides hardware control capabilities such as power on and off, set next boot device, operate the identify light, and other operations. It provides access to telemetry data such as power or temperature or other sensor data. It provides health information about whether systems are healthy, and if unhealthy, what is the reason for the unhealthy condition. Inventory data such as serial number, MAC address, drive information, and so forth, as well as performing firmware updates and firmware configuration such as BIOS settings and BMC configuration. It provides for OS deployment to disk or, in the future release, diskless boot, which will be mentioned later. It provides console management and access through either the command line or the web interface, as well as an ability to log all console data if desired. It provides an API to access an aggregation of network switch information, such as MAC forwarding databases and LLDP neighbor data. It provides a command line interface for interactive use and scripting, a REST API for those who would prefer to use Python or some other HTTPS client to make calls, as well as a web interface. Broadly speaking, it's our take on what XCAT 3 would have been. First, we want to continue what's been working well with XCAT. To start, we have a similar command line interface with facilities to analyze the consistency of output and to take output that's different and highlight how it's different. We have a similar node range syntax that can quickly describe large number of systems based on groups, sequential ranges, database queries, and set arithmetic to combine them. We also have a similar database structure with group inheritance, with the capability of using expressions to expand and derive unique values based on other fields, numbers from the name, arithmetic manipulation of that data. We wanted to go beyond what we were able to accomplish in XCAT. We have a stronger and more powerful node authentication strategy, leveraging the server TPM where possible. We support Secure Boot being enabled for most configurations and OS versions. We have a hardened facility for protecting credentials that we use to connect to network switches and BMCs and other devices. We implement a secure shell PKI to provide us more capability while also eliminating the need for us to transfer any private host or user keys. We support fully validated HTTPS for OS deployment. We have better hardware management capability with more information, as well as the ability to update firmware and configure the firmware without use of any closed source dependencies. We've implemented a number of ease of use enhancements. We have a simplified configuration with fewer settings required to be set, thanks to more reasonable defaults and auto-detect capabilities. We have rich tab completion in our command line interface. We have API browsers for the command line and web GUI. And we also have a web interface with rack view with temperature overlay, as well as the ability to open up multiple consoles and to broadcast keystrokes to all of them concurrently. And everything we do is built consistently upon a common REST API for all the web and command line function. We worked on interoperability. Confluent can coexist with an unmanaged DHCP server, or the user can skip having a DHCP server entirely, even as we support Pixie Boot. Confluent can perform OS deployment, or it can be used to set up other software for OS deployment using Confluent's onboarding capabilities. More data is exposed to the user for use in their own software to implement automation that may not be addressed by Confluent itself. Confluent supports Ansible playbooks during OS deployment as well as its own scripting facility. We dramatically improve performance. We can support many more requests than we were able to do in XCAT concurrently, as well as continuing to support the large requests that we did in XCAT. We have improved scale-up capabilities. Confluent's collective mode has enhanced security, it's easier to set up and use, and has reduced external dependencies to work in a highly available fashion. We also want to provide a better scale-down experience. We don't require a private network, although we do support them. We have better coexisting with existing networks, and we require less configuration, so it's worth it even for fewer systems being configured. We've made improvements to the OS deployment capabilities. Our OS deployment profiles are now file system centric. We don't have database hosted metadata, so OS profiles can be moved between hosts much more easily. In addition to Pixie, we also support UEFI HTTP boot and virtual media boot with an optimization to support a single boot image for an entire profile, no matter how many nodes are associated with it. Confluent has a very sophisticated discovery facility for onboarding systems. It's able to take unconfigured hardware and quickly onboard it without any crash card activity or other tedious manual activity. It's able to remotely detect and configure BMC class devices even if the host is off, so we don't have to wait for a Pixie boot to begin discovery. And we support several methods. We can either have the user interactively use the command line or interact with our API. We have a built-in facility for processing a spreadsheet of either MAC addresses or serial numbers and using that to drive the ultimate node identity. And we can do this based on where devices are physically connected to Ethernet switches or into chassis. And of course, the discovery process is optional and may be skipped if the user prefers another strategy. So here we can see that we can detect nodes that have Pixie booted and show the switch and port. And now we will define a node and manually assign based on serial number, and this will configure the IP address, username, and password for that system, enabling us to be able to run power commands and health commands and any other commands we may want. Now we're going to demonstrate the location-based capability. So define 9 through 12, and the dense group provided the topology information. So now we request a rescan, which will kick off the automatic process. Now we look and we can see that D9 through D12 now exist and are properly configured, and they're also able to support Pixie boot by virtue of that activity. And we can execute BMC management commands. In 3.3, we plan to provide stateless support. We want to provide an easier build process. The resultant image will be more portable, so it can be moved easily between systems with a strong segregation between distribution content, site-specific information, and Confluent add-on content. We want to provide easier access to run an image as a container for the purpose of modifying it for ultimate final boot, and make it more natural to produce the correct init ramfs without the user actually having to request it explicitly. And we want to support either build from scratch or to capture from an existing installed system. So here's what it looks like to build an image with the 3.3 support. And now we will run it as a container. Here we could update kernel or install drivers, any number of activities. And finally, we pack it to produce the bootable stateless image. We provide multiple deployment options. This system can be boot tethered. This provides highly available multipath HTTPS so that the file system can be accessed on demand rather than downloading it up front to minimize memory consumption. We also support untethered diskless. This would download the file system to memory with a higher memory consumption with a slower boot, but it will produce reduced sensitivity to network conditions. And finally, the ability to install these to disk. And here is an example of a system booting the tethered diskless mode with multipath support for the HTTPS image. Here we're using Secure Boot over HTTPS. And the driver's initialized to get to access the network. And we found a number of paths to get to the same root file system, and we are in the OS. And now we're able to SSH in, and we can see the amount of free memory. And we can see that the memory used is largely evictable. And we have the SSH PKI set up so that node-to-node SSH is enabled without any contents in the SSH directory. We also have a persistent limited SSH to the fully untethered stateless, even if we boot in a tethered mode after the system has been booted for diagnostics and recovery. So if you SSH to port 2222 as root from a deployment server, you'll be able to access a system that doesn't have any other accounts and it doesn't support any password login. In addition to being able to boot over PXE or HTTP boot, for Lenovo hardware, this can be installed directly onto the XCC, so a diskless node can have a local copy of the bootstrap portion of the stateless image. More information, including more documentation and downloads and YAML repositories, are available at hpc.lenovo.com. And thank you for your time.